Okay guys, so let's start finally. I apologize for the delay. Okay, so we were talking about the GARCH type processes, and we stopped basically in chapter 6.5, basically the estimation and testing. Okay, so how does it work? Okay, so we assume, okay, so the first thing is that, okay, estimation and testing. And this means the following, okay? So basically we assume that the noise is assumed to follow the normal distribution, okay? So here in this case, the white noise is basically assumed to be normally and independently distributed, okay? Here, in this case in particular, we mean zero invariance. One, okay, so the noises are normally distributed, and so therefore we basically use the maximum likelihood estimation, okay? Likelihood estimation, okay? Now the maximum likelihood estimation is about maximizing the so-called likelihood function, and the likelihood function will be the joint distribution function, okay? So this means that maximizing the likelihood function, okay, good function, okay, is the joint distribution function, okay? So joint distribution function of the observations, okay? Joint distribution function, okay, of basically of the observations. I mean, regarding the observations, what we do is basically we break it down to the increments. So the increments of the process are asymptotically normal, let's say the so-called, they're corresponding transformations, let's say, depending on the model. Okay, so we basically talk about the GARCH type model. So this is basically how it's done. Okay, so the joint distribution function is basically set up, and the processes, the parameters of the process are estimated in such a way that the parameters are maximized. The likelihood function is maximized with respect to the parameters. So the likelihood function is maximized, okay, with respect to the parameters, okay, to the process parameters, okay. So depending on the model you have, okay, that's basically how it's done, okay. And so based on the normal distribution of noise, we establish now the following asymptotics, and that's what we would do, okay. Okay. Now, what we basically do here, in terms of parameters, for instance, the first thing is what we do here is testing the autocorrelation of the squares. Okay, so that's the first one. Okay, so autocorrelation. Okay, of the squares. Okay. So that's basically the first type. Okay. So as we talked about it later, previously yesterday, so if we have a GARCH process, and this implies, okay, an ARMA process of the squares, okay. So you basically have that, okay. So if basically you have a GARCH process, then the squares of the process follow an ARMA model. Obviously, we will have talked about it. So, in basically the autocorrelation here of the squares, here of the sample, imply or indicate GARCH, the presence of GARCH effects in data. Okay, so autocorrelation of the squares. Okay. indicate the presence of GARCH effects, okay, in the data. Okay, so GARCH effects in the data. Okay. I mean, I'm talking about in terms of the original data. Okay, so this is basically the original data. Okay, and so therefore, I mean, you have the autocorrelation of the squares. This is what we were talking about here. Okay. So we take the square of the processes and test for autocorrelation. That's basically what we do, as I told you before. Why? Because GARCH implies an automoble of the squares. Okay, so that's how it's done. Okay, that's relatively easy. So then you would be able to examine whether or not there are GARCH effects in the data. Okay. Now, okay, so we basically, I mean, we have two tests that we can apply. Okay, so the first one was being Stochastic test, and the second one was the Liouville-Box test. Okay, so I mean, this is depending on the test statistic. Okay, so the Null hypothesis is always the same. Okay, so the Null hypothesis is basically, let me just emphasize here. Okay, so basically that you have the autocorrelation function of the squares with respect to time leg 1, okay, is equal to the autocorrelation function of the squares, obviously, of time leg 2, etc., etc. And the last one is doing the autocorrelation of the process, okay, at time leg m here in general. Okay, so you can test basically m does not needs to be equal to the basically to the order of the process. Okay, so it could be also something else. You can test it separately. Okay, independently from the model that you basically choose. Okay, so again we have the autocorrelation of the squares. Okay, indicating GARCH effects in the data. So if basically the autocorrelation is equal to 0, so the Null hypothesis says that the autocorrelation is 0, that basically means that there are no GARCH effects in the data. And also basically that means that there is no volatility clustering or anything of that kind. Okay? And the alternative hypothesis says that basically there is at least one autocorrelation function which is not equal to 0. Okay? Obviously. Alright, so that's basically the negation, okay, of the Null hypothesis, obviously. Okay, so meaning that there is at least one autocorrelation which is not 0. Okay, so along here from these autocorrelation functions. Okay, now we calculate the so-called empirical autocorrelation. Okay, so this will be the empirical autocorrelation. This is done as follows. Okay, so empirical autocorrelation of the squares, okay, of the squares. Typically, let's say, for instance, for time leg h, okay, so here you have the autocorrelation of the square, okay, and you calculate the autocorrelation as follows. Basically, I mean, you replace the theoretical one with the sample analog. Okay, so here, of course, I mean, you would have, I mean, just you leave out the means and just have the sum. So okay, so here below you basically got t times the variance. Okay, so you have yt squared minus, and here you have y squared bar, which is the mean. Okay, so basically this is the sum of the squared, you know, I mean, that's basically what you would have here. And you take the square here. So the sum of the squared distances between two squared observations, let's say. Okay, so y squared bar is basically the arithmetic mean of the squares. Okay, so I will add this here as an explanation first. Okay, so y squared bar is the mean of the squares. And the mean of the squares is calculated from the sample as follows. So you have 1 over t times the sum of the squares. Okay, so 1 over t times the sum of the squares of all observations. Okay, so basically you assume that you have a sample. Okay, so the sample that you have is basically y1, y2, etc., and y capital T. So these are your sample observations basically of the process. Okay. Now first basically you calculate the mean of the squares. This is the mean of the squares, and then you put that here into the sum that you see here. So this is going to be the sum of the squared differences of the squares. Right? So of the squared observations. Okay, so this is the squared observation, and this is the mean of the squares. Okay, so that's going to be basically, I mean, relating to the variance of the squares, let's say. Okay, and in the numerator, you're going to have the autocovariance of the squares. So there may be a simplified version of it. So here, because some of the summands fall out, so you have here you start at t is equal to 1, and the final one will be capital T minus h. All right, so h is basically the time lag that I'm using here for this autocorrelation. Okay, so h is going to be the time lag of the autocorrelation, and that will be the final one here in the sum. You're going to see this. Okay, so basically you have yt squared minus y squared bar, so the mean of the squares here, and then times you have yt plus h, all right, squared minus the mean of the squares. Okay, it doesn't matter that basically here the sum of the numerator has fewer summands than the sum of the denominator, so it basically doesn't make any difference. Okay, usually, I mean, if you had the empirical variance, you would divide here by 1 over t. So if you had 1 over t here, then you would divide it basically by the empirical variance, but this is just basically simplified this way. Okay, although you have, let's say, fewer summands here of the numerator, because the sum starts at 1 and you have t minus h. Okay, so depending what h is, okay, so basically you will have that in the numerator has fewer summands than the denominator, but it doesn't matter. So that will be the empirical correlation. Okay, now you calculate that from the sample observation that you have here, and you do the following. So you do this for, like, you know, depending on your age. So you can do this, and what you would do, I mean, depending on the null hypothesis, that you would say that age is, okay, you have 1 and m. Okay, so you calculate this for all values, for all autocorrelations that you consider here in the null hypothesis. Okay, so from 1 till m. Okay, so not just the 1, not that it's a first empirical autocorrelation, but also you got here the autocorrelation with respect to the time lag age. Okay, so an age is going to be something between 1 and m, obviously. Okay, so the number of empirical autocorrelations that you calculate is equal to m, depending on the null hypothesis that you're testing. Okay, so I mean, you have two different test statistics, and both follow the chi-square distribution, as we've seen this in the previous chapter before, but you can choose any of the two. So Box-Pierce, okay, so first this is the Box-Pierce test statistic, okay. And the Box-Pierce test statistic, I denote this by QM, okay, so M is basically the maximum time lag that you use for testing the autocorrelation, okay. And this will be equal to, and then you will, okay, so first what you do is you take the autocorrelation, okay, and then you calculate the square of it. So basically you have the squared autocorrelation, okay, and then you sum it up. okay, with respect to h. So h is here equal to 1, okay, so that's why you start. And the final one will be m, and then you multiply this by capital T, okay? And as we've seen in the previous chapter before, of course you take the empirical one, as we've seen in the previous chapter before, this thing converges in distribution towards the chi-square distribution, okay? So towards the chi-square distribution with m degrees of freedom, so the number of degrees of freedom is equal to m. Okay? And the reason for being that is because that these expressions are, okay, so these expressions is correct, and distribution divided by capital T is going to be asymptotically normal. Okay, so that's what you're going to get here. Alright, so this thing is going to be asymptotically normal, okay, as basically the number of sum and grow. Okay, so there is also the modified Oxford statistic, okay, which is, I think, more practical. So this is going to be the Liouville statistic, okay. And I'm using a different notation here. Okay, so for the Liouville statistic, I used in the lecture notes the notation Q tilde. Okay, so Q tilde here. Sorry, given the autocorrelation with respect to the time lag t. Okay, so here in this case, I mean, it takes into consideration if, let's say, the number of summations or the summands here in this part, if you know the time lag is large, okay, then the asymptotics are quite difficult to handle with. Okay, so in this chiral distribution, so this will be a little bit faster in this case because it takes that into consideration. So that is basically more accurate for larger time lags. Okay, so you have t plus 2, okay, times the following sum. Okay, so basically you sum up the squares of the autocorrelation 2. Okay, but what you basically do is you divide them by t minus h. Okay, so here basically you will have also the squares of the autocorrelations. Okay, so we're talking about the empirical autocorrelations, okay, of the squares of the process, basically. Okay, so this is the square, okay, and you divide this by t minus h. Okay, so this is how the statistic will look like. Again, this takes into the consideration that, you know, if the time lag is too large, then the autocorrelation estimate would not be that accurate, okay? Because, I mean, of course, the sample observations are limited. Usually, we would have that the number of observations that we use in a sample exceeds, let's say, the number of the autocorrelation time lag, okay? And now that also converges in distribution to the chi-square distribution with m degrees of freedom as well, okay? But let's say the second part is applied in case that basically the time lag is relatively large, okay? Because if the time lag is again relatively large, then the empirical autocorrelation estimate would not be accurate, let's say, okay? I mean, if it's relatively close to capital T. So that's why it's modified, let's say. Okay, so the null hypothesis that there is no autocorrelation of the squares of the observations can be rejected at level alpha if basically, I mean, the critical value is of course 1 minus alpha quantile of the alpha distribution, so it's going to be the critical value. Okay. Okay. So the critical value is of course 1 minus alpha quantile of the chi-square distribution with m degrees of freedom, okay? So this is the 1 minus alpha quantile chi-squared distribution with m degrees of freedom. Okay, so what you do is basically you calculate either the box-Pierce test statistic or the leading box test statistic, and you look whether or not this is greater than the 1 minus alpha quantile of the distribution. So you reject the null hypothesis, okay? If basically, I mean, either, let's say we look at the box-Pierce test statistic, so if the box-Pierce test statistic is greater than the 1 minus alpha quantile of the chi-square distribution with m degrees of freedom, okay? So this is rejected, okay? So at level 5%, okay? Most cases, okay? But here in this case we have level alpha. So alpha is some, I mean, practice it's either 5 and 1%, depending on the model that you use, okay? So if the null hypothesis is rejected, then basically this means that the data exhibits, okay, so I'm talking about these observations, okay, so this is the data, okay, so this is the sample that you have, okay, so the data exhibits GARCH effects, basically, okay, so there is empirical evidence for the data to exhibit GARCH effects, so stochastic volatility, let's say, okay, basically meaning that there is autocorrelation of the squares. Sorry, this is not the squares, this is the data. Okay, so the data is here. Okay, this is the data that we're using. Okay, sorry, where I got it here. No, there it is. Okay, so this is the data. Okay, this is the data, obviously. Okay, and here we have not the data but the squares, so we can look different colors. Okay. Okay, so the squares are here. These are the squares. Okay, so hopefully you see it better now. Okay, guys, so that's basically it. Okay, that's what you do. Okay. All right. And on the other hand, so this is, I mean, the same principle applies here. I mean, you would get basically the second alternative. So what you do is, okay, so that's going to be a new alternative. Yes, you got a question? Yeah. Yeah. Yeah, sure. Okay, sorry. Okay, so the second alternative is basically you would perform a regression of the squares. Okay, so that's basically using the autocorrelations. And what you also can do is, okay, so this is going to be the second alternative. So you estimate the following regression model. Okay, so what you do is, okay, so I mean we have seen that if the data exhibits these kind of effects, then you can write the function in terms of the autoregressive process. Okay, so that's how you do it. Okay, so here in this case you would have alpha 0 plus alpha 1 times the square of yt minus 1 plus alpha 2 times the square of yt minus 2, etc., etc. And the last one will be alpha q times yt minus q squared, and then plus epsilon t. So this is the regression model that you estimate, basically. Okay. All right. So you estimate the model, and then you take the coefficient of determination. Okay. So r squared will be the coefficient of determination of the model. Again, so the coefficient of determination, you had to see for this assignment already. So this is basically the ratio of the explained variance of the model. Okay, so the explained variance here of this expression. Okay, so this is the dependent variable. So you take the explained variance of that variable divided by basically the total variance of the variable. Okay, so this is how it works. So you calculate the coefficient of determination of that. And then what you do is basically you take the following test statistic, and what you have is that n times, okay, so n times the coefficient determination will converge in distribution towards the chi-square distribution, okay? But here again we have q degrees of freedom, okay? So the model lag is basically equal to the time lag of the autoregressive process, okay? So n times r squared is basically converges, or that converges in distribution towards the chi-square distribution with q degrees of freedom, okay? And n is the number of observation pairs, okay? So all observation tuples that you would get basically here from the process. So n is not equal to capital T, of course, all right? So depending on basically the process what you have, so the sample, okay, so the sample size is again capital T, all right? So you have, and basically a y1, you have y2, y3, and so forth, right? Okay, so, and y capital T, okay? So the sample has T observations, all right? But the number of observations is not equal to basically the number of observation pairs that are considered in the regression model, because it depends on the time lag, okay? So if, let's say, if you have a first order autoregressive process, then the number of observations will be equal to t minus 1, okay, because one observation is basically don't have a pair, so that, you know, cancels out. From the regression, it's not considered if you have a time lag of 2. So basically then the number of observations that are considered here in the regression is equal to t minus 2, also capital T minus 2. So in that case, obviously, if the time lag is equal to q, then you would have that basically that n is equal to t minus q, obviously. Okay, so t minus q are the number of observations that are considered. Okay, depending on the regression. Okay, now, so you can reject the null hypothesis. Okay, if the model is not significant, because the null hypothesis says that all coefficients are equal to 0. Okay, so without exception. Okay, so here the null hypothesis basically says that the coefficients, these alphas, okay, so alpha 1, alpha 2, and so forth, okay, so here you have alpha q, all of these coefficients are equal to 0, okay, so that's what the null hypothesis says. Of course, the alternative is basically the negation of the null hypothesis, so basically it says that at least one of the coefficients is not 0. Okay, so if at least one of the coefficients is not 0, that means that the model is significant, let's say. And if the model is significant, that means that there is an autocorrelation of the squares. And if there is autocorrelation of the squares, that this might indicate that the original data has GARCH effects. Okay, so as soon as the autocorrelation of the squares is significant, then basically you would find that the data exhibits, or that might indicate that the data exhibits GARCH effects again. Okay, so, and of course the test statistic is basically used by the coefficient determination. So you can reject not the hypothesis. Okay, if basically, I mean, this is what you would obtain from the asymptotics. You would reject the null hypothesis if the test statistic, which is equal to n times the coefficient determination, is greater than the chi-square distribution, or 1 minus alpha quantile of the chi-square distribution with q degrees of freedom. Okay, so again, so this is the 1 minus alpha quantile of the chi-square distribution with q degrees of freedom. Okay. Analogously to the previous section where we had basically m degrees of freedom. That is the lag order of the autocorrelation. Okay, so you can use either, I mean, the two processes, I mean, the two tests are relatively similar. Okay, the assumptions are, the asymptotics, let's say, are different depending on the characteristic of the process. In normal case, it doesn't fit, let's say, 100%. Okay, so basically, in order to make sure that these effects are significant, what you would do is you would do both of them. Okay, so you would apply both tests, not just one, but both. Okay, so either, let's say, the box Pierce or the leading box text, and then you would also test the full significance here of the autoregressive model. Okay, so this is basically what it is about. Okay, so that's how you would test these GARCH type effects that you would maybe examine. Okay, that's it. So this is something that you could also use in the paper. Okay, so if you want to apply this, or you could, I mean, you will see probably this in the exam. So what I would do here in particular is, for the examination, is basically I would give you an output, okay? And I would, you know, let you answer the question whether or not the model is significant, as you might see this in the exercises, okay? So I would estimate the model, and then you would just examine that, okay, whether or not the model is significant. That would be it, okay? So no big deal, let's say, all right? Okay, you get, of course, the distribution tables. You still know how the distribution table works, right? Okay, of the chi-square distribution, more or less, let's say. Okay, maybe I suggest that next week we look at these distribution table stuff, whatever, okay, some more detail, okay, I think. But you've seen this already, so one time, so at least, no, I hope so. So basically, I assume that it will not be a big deal. Okay, but I provided you, of course, with the distribution tables. So next week we're gonna practice that a little bit. Okay. So what I don't do in the exam is I do not consider, like, say, formula deliberation. So let's say, I mean, show this and that. For instance, exercise 6.3. You don't have to do that. So that's not going to be part of the exam. Okay, we do this here because I think that this is, or this might be too difficult for the examination. Okay, still. But what I could do is, let's say, for instance, I could, let's say, give you some model parameters. So I would set up some model parameters, and I would say, okay, calculate the long-run variance of the process. Okay, and there is a formula here in the lecture notes for the long-run variance. So all you would do is just basically you just plug in the corresponding parameters of the long-run variance, and that's it. So basically no proofs, none of that stuff. Okay.
Do we have to know all formulas?
No, you don't. So of course, you can bring some notes.
Yeah.
Okay. Yeah. So you will be allowed to bring notes into the exam.
Like anything?
Yeah. I mean, I'm not sure. I mean, it depends on you guys. I mean, first I wanted to basically let you or allow you to use the lecture notes, but I think it's going to be too long. So. Okay, so lecture notes will probably be like, by the end of this course, so it's between 70 and 80 pages. I'm not sure it will be a help. So either I choose, the lecture notes, so you're supposed to bring a printed version of the lecture notes, okay? I cannot print that for you, okay? I don't know, I mean, I could, but I don't want to, okay? So 20 times 80, it's equal to 1,600. So this is not covered by basically my loan here. Anyway, but or the other option would be you bring, like, let's say 5 or 6 pages of your notes on your own. So you choose yourself. I mean, I don't know which version is better for you. Maybe you can think about it. Okay, so basically, I mean, the lecture notes contain everything. Okay, so all you need basically is that. Okay, so it doesn't include the solutions to the exercises. Okay, so what you would do is just, bring a printed version of the lecture notes, or either I let you, let's say you have five sheets of notes of any kind that you want. Okay. I mean, I don't know which version would you prefer, guys? To be honest.
The last one.
The second one. So you bring your own notes. Okay. All right. Is that okay for everybody? What about the ladies? What do the ladies prefer?
I prefer the lecture notes.
You prefer the lecture notes? Okay. Now I'll let you decide. Okay. So I set up a poll. Then let you decide afterwards. Okay. I mean the lecture notes are complete. So maybe I'll let you both anyway. So it's not a big deal. Okay, guys. I mean there are lots of formulas. So we have seen some. So basically. It doesn't matter. You can make your own some notes. So I'll allow you to bring the lecture notes and to make some notes. Okay. So that would be. Yes.
You're allowed to do both.
Yes, you do both. Okay. So I don't have time to walk around and check out these things. So you can use notes. I mean, if I prepare the course, I will make the notes. I did the notes also. So why wouldn't you, right? Okay. But anyway, okay, so there is of course a printed version, so you can use a printed version or basically some extra pages. Okay, and I will include some extra pages, okay, into the printed version, some empty pages, okay, and then you use the empty space for your own notes as well, okay. So, okay, let's do this, okay. But I didn't finish the lecture notes yet, so I'm just about to write the last 2 chapters, okay? So it will take a little bit, take more time, so don't start printing it. Okay, and maybe we'll find some errors in there anyway. Okay guys, now let's check out the exercises. Okay, so I'm talking about the exercise of chapter 6.1, 6.2, etc. Okay, so basically we were doing 6.1 already. Okay, so that's okay, so 6.1 is, okay, maybe we can do this again. So this is exercise 6.1. Okay, so what we have here is the stochastic volatility process, okay? And what you need to show is, basically that the variance of the process is equal to the expectation. Okay, so so here you have, this is the noise, alright, so here you have the white noise. The noise does not need to be normal, but here you have that sigma squared is a stochastic process. Okay. And here in part A, you need to show that basically that the variance of the process, the variance here of the process is equal to the expectation of sigma squared. Okay, that's going to be the first one. So basically, this is the general type of let's say the class of stochastic volatility processes. Among others, the ARCH and the GARCH type are also part of that. So that statement is always true for any of stochastic volatility process, for instance, for the ARCH or for the GARCH type anyway. Okay, now that's not difficult. Okay, so I think we already did this, but let me just do this again. Okay, so that's the first part basically. So what you would do is you would calculate the expectation. Okay, so first off the conditional expectation. Okay. All right. Or we can start with the variances here. It's relatively easy. Okay, so the variance of the process is basically equal to the expectation of the squares. Okay, the expectation of the squares minus the square of the expectations. Okay. So that's where you would start. So the expectation of the squares minus the square of the expectation. So we have no square here, sorry. Again. So, and of course, this is going to be equal to, let's cement effect here, this part is going to be equal to 0. Okay, so basically the variance of the process is equal to the expectation of the squares, and of course the expectation of the squares is going to be just, I'm taking the square of this process, so this is going to be equal to the expectation of sigma squared times the square of the noise. Now, of course, these two are independent from each other. So due to the independency, you have that the expectation of the product is equal to the product of the expectations. Okay, so the expectation of the product is equal to the product of the expectations because these two are independent, so the noise is independent here of sigma squared. Okay, so that's what you would have. Okay, and basically, I mean, this here is equal to 1, of course, by assumption, because the variance of the noise is equal to 1, obviously. So the variance of the noise is equal to 1, and the expectation of the noise is equal to 0, right? So in that case, this expression is equal to 1. So finally, you would get that the variance of the process is equal to the expectation of the square of sigma, obviously. Okay, so that's relatively easy. All right, the second part of the exercise is that, let me just go back to it, okay? You have an autoregressive process of the squares, and then you would show that basically that the conditional variance, okay, so here in this case in particular, you would have an arch cube, you have an arch cube type process, okay, so basically y is equal, y follows an arch type process, okay? So what does it mean? Basically, it means that the following, so you have yt is equal to sigma t times the noise, okay? And where sigma squared is equal to basically alpha 0 plus alpha 1 times yt minus 1 squared plus blah 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 plus alpha cube times yt minus 2 squared. Okay, so that's what an arch process is. And here you need to show that basically that the conditional variance of the process is equal to sigma squared. Okay? Right? So again, the unconditional variance is equal to the expectation of sigma squared, and the conditional variance here in this specific type of process is going to be equal to sigma squared, basically. Okay? So that's how you would, what you would do. So what I'm talking about is you calculate the unconditional variance of the process, so the variance of the process given its past, okay? So given its past, okay, so I use yt minus 1, yt minus 2, etc., etc. So all observations of the past, let's say, are available. What would be the variance of the current observation given the past of the process? Now, that is of course equal to, the variance is equal to the expectation of the squares minus the square of the expectations, okay? So the expectation of the squares, okay, of yt, so you have the expectation of the squares given its past, okay, so yt minus 1, yt minus 2, etc., etc., and then minus the square of the expectations. Now, of course, you have that basically the stochastic volatility process is marking a different sequence, so the condition expectation will be equal to 0, but let me just here write it, so the expectation, or the square of the condition expectation, here in this case, okay? So, and then you take the square, right? So the expectation of the square minus the square of the condition expectation will be equal to the variance. Now, of course, this is equal to 0 again. You have seen this quite often. Okay, so the conditional expectation is equal to 0. So basically, the variance will be equal to the expectation of the square of the process. Now, what is going to be the square of the process? Again, it's just the same thing. The square of the process is going to be equal to, you have sigma squared, okay, times the noise squared, because the process is basically equal to sigma times the noise. So if you take the square of that, then it's going to be equal to sigma squared times noise squared, given the past, okay, so given the past of the process yt minus 1, yt minus 2, etc., etc. All right? Now guys, the function, the expression here, sigma squared, right? The expression sigma squared is basically a function of yt minus 1, yt minus 2, etc., etc. So this is basically a function of the squares of the paths of the process. So that means that this expression is already a constant because, you know, the path is given. So the path is given, so these things are also given, right? These things, so I'm talking about yt minus 1 squared, yt minus 2 squared, etc., etc. So this is all given, so in that case the volatility is also given. Sorry, I forgot to denote an index here, so this is going to be sigma squared t, of course, okay? So as soon as the path of the process is given, sigma squared is also given, which means that this is a constant, so expectation of a constant times a random variable is going to be equal to basically the constant times the expectation of the random variable. Here you have a linear transformation of the random variable, okay? And the expectation of a linear transformation is equal to the linear transformation of the expectation. So this is going to be equal to sigma squared times the expectation of the noise. Okay, so times the expectation of the noise given the path of the process. Okay, now the current observation of the noise does not depend on the path of the process, basically. Okay, so that's quite obvious. So the expectation, so the conditional expectation will be equal to the unconditional expectation. And the unconditional expectation is going to be equal to 1, of course, because the variance of the noise is equal to 1. Again, so the variance of the noise, all right, is equal to the expectation of the squares minus the square of the expectations. Okay, and of course the expectation of the noise is equal to 0, so that's why the variance of the noise must be equal to the expectation of the square. And the expectation of the square is equal to 1 because the variance of the noise is equal to 1, so by definition. So basically, I mean, that's going to be it. So the conditional variance, okay, is basically equal to sigma squared, and this can be time dependent, although the process is or can be stationary, guys. Okay, so don't forget this. Okay, so the conditional variance can be time dependent, although the process is stationary. That's why it's called autoregressive conditional heteroscedasticity, because the variance, the conditional variance, can depend on time. Okay, so I mean, we have seen this quite often, but let me just summarize this. Okay, so the conditional variance, okay, variance can depend on time, right? Although the process might be stationary. Okay, so so the process might be stationary. That's where basically the name is coming from. Okay, autoregressive conditional heteroscedasticity process. Okay, good. Now that was basically part B, and that should be also true for the GARCH type process as well. So this is part C of the exercise. Okay, so here in this case, you would have a GARCH model, and for the GARCH model, the conditional variance will be also equal to sigma squared. Okay. Now, what does it mean basically that you have a GARCH model? So basically, it means that you have, okay, so yt is equal to sigma times the noise, where basically sigma squared is equal to, I mean, you have the autoregressive part, so alpha 0 plus alpha 1 times yt minus 1 squared plus blah 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 plus alpha cubed times yt minus q squared, okay? And then you have the moving average part of the noise, remember, okay? So the moving average part of the noise, I mean, basically are depending here on the sigma squared. This will be equal to, so you have beta 1 times sigma squared times t minus 1, okay, etc., and then you have beta p times sigma squared of time t minus p. Okay, so this is how the GARCH process will look like. Okay, now here you would get the same thing. Okay, so that's going to be the same as well. Okay, so basically no difference here in this part. Okay, absolutely no difference here. Okay, so here for this case, this is going to be also equal. So the conditional variance, okay, is basically also equal to sigma squared. Again, absolutely no difference. Okay, so this part. All right. So this was exercise 6.1. Okay. Again, I mean this is relatively easy. Okay, so still, but I will not use this in the exam. Okay, I think. So things like that will not be relevant. Okay. So more like the application part. That's how I would cover basically also your seminar papers as well. Okay? So according, I mean not specifically, you know, I would give you the certain output and everybody has to know everything. So in this case, you know, basically what we talk about in your seminar papers are going to be your results. Okay? So not a big difference. Okay? Good. Now let's consider exercise 6.2. Okay. Okay, so basically we have to prove that if the process is stationary, then basically that the sum, okay, so let's say if ARCH process is stationary, okay, that this implies that basically that the sum, okay, of these coefficients that the process has, okay, so this is the ARCH-Q process, is less than 1. Okay? So where does it basically come in from? Okay? Now, we were looking at this too, okay, but you can see this. So basically what you would do is, let me just, calculate basically the expectation of the process first. Okay, so the expectation of the process, we have to show that this is stationary. So if it's stationary, then it's going to be the same thing. Okay, so the expectation of the process is going to be equal to the expectation of sigma times the expectation of the noise, and of course sigma basically noise is independent. Current observation of the noise is independent of sigma. So basically the expectation of the product will be equal to the product of the expectations. Okay, and the expectation of the noise is equal to 0 by definition. So basically then this expectation will be also equal to 0.